All right, well, good evening, everyone. Thank you for coming. As Selena said, my name's Tom Rayment. I'm Doug's Chief Geo, head of our research team. And this is a talk on what we believe to be the future of seismic processing and imaging, which is multi-parameter FWI imaging. I realize that's quite a big claim, so hopefully I can convince some of you that that is indeed true tonight. But before we look forward, let's look back at the history of seismic imaging. So it was known that events were mispositioned from the early days of seismic exploration back in the 20s, but it wasn't really until 30 years later, in the 50s, that imaging really began in earnest. And that was performed manually by migration machines, a picture of which we have here. The advent of the computing age and the digitization in the 60s resulted in an enormous amount of research and development of various imaging algorithms through the 70s and 80s from people such as Claerbout, Schneider, Stolt, Gazdag, to name a few. But the processing power was small by today's standard, and so 2D post-stack migration was about the limit in the 80s, and it wasn't really until the turn of the century that there was sufficient affordable compute to be able to perform pre-stack 3D migration, for example. Now, algorithms like RTM was first attempted in the 80s, but has only really been run routinely in the last 10 or 15 years. And so again, there's this 30-year gap between theory and practice because of the compute requirements demanded. Now, in the last few years, iterative least squares migration has become possible and is regarded as one of the most advanced and conventional imaging algorithms that we might run today. But all of these approaches share a common theme. They can only image primary data. And so we have to process the field data through an extensive pre-processing sequence to condition it and attenuate parts of the wave field that we can't image, such as ghosts and multiples. So what I'm showing here is a pretty standard marine processing workflow. And as we know, it can often take many months, potentially even years, to get from the field data to an image product because of all these steps that we have to go through. Now let's switch our attention to full waveform inversion. The idea was first formalized back in the 80s with the first attempts in the 90s, but again, it was about 30 years or so before diving wave FWI for model building became a reality on production projects. And this is now very common, of course. In recent years, there's been a switch of focus to the use of reflections in FWI. And that gives us an opportunity to try and bring these two strands together and use FWI for imaging, which is now a very hot topic in the industry. Now, FWI is in essence a fairly simple process. We begin with some initial Earth models, and then we simulate the seismic experiment in the computer. And this generates primary, multiple, and ghost reflections within our synthetic shots that we can use to compare to the real seismic data, the field data. And from there, we can use any discrepancy to update our models. And then we iterate, running the same process dozens or even hundreds of times. And as I said, this is now we're very used to focusing on diving waves to generate velocity model updates with this technology. But we can use the reflections, and since FWI is modeling the full wave field, including the multiples and the ghosts, that means that rather than removing that data, we can actually use it in this algorithm to generate updates of our Earth models, including a reflectivity volume. And that's the essence of FWI imaging. Now, there's different aspects that we need to consider when we're using reflections in FWI. So typically with diving wave FWI, we're really interested in the kinematics, the movement of those diving waves, and trying to match our synthetic to our observed data and update our models accordingly. We don't tend to care too much about the amplitudes. We might use normalization schemes to deal with that. But if we're using reflections and we want to use them properly, then we have to consider those amplitudes, which are the dynamic effects in the wave field. So we have the kinematics, which are controlled by wave transport, so velocity and anisotropy models, for example, and then the dynamics which are caused by scattering interfaces. And these are the two aspects of the reflections that we need to focus on. Now, a common approach in FWI imaging is to simply open up the in diving wave FWI, let the reflections into the update, And this combines the kinematic and dynamic effects into a single output, what I've called a velocity attribute. You could call it a pseudo impedance volume. This was something that we were actually doing about 5 or 6 years ago, and we were saying to clients, well, you could use this velocity attribute to try and interpret the data you get from the field data to an interpretable product very quickly. And we got quite a lot of pushback at that time saying, well, it's not a true velocity model. There are other effects in there. And so that sent us down a different path that we'll get to in a moment. Now, recently, this has become a fairly standard approach to FWI imaging, and by taking a derivative of these attributes, you can get a pseudo reflectivity volume. And this is an approach that I call single parameter FWI imaging. There's been quite a lot of nice examples of that approach. But because of that response that we got to this approach, we went down a different path and we decided, well, how can we resolve this crosstalk issue between the kinematics and dynamics? How can we get an accurate velocity model? And how can we also get an accurate reflectivity model? So we have to overcome this crosstalk issue between the kinematics and the dynamics. Our experience of this approach is that those velocity attributes can give you these nice reflectivity results, but you don't necessarily get an accurate velocity model update, and often requires extra passes of tomography. That's usually because of assumptions that are made about density. So our approach since then was to focus on how we solve this crosstalk problem, and what we've developed is something that's called multi-parameter FWI imaging. And this approach, we simultaneously determine at least 2 distinct outputs, a velocity model and a separate reflectivity model. In fact, we've published a paper where we inverted for 3 outputs, velocity, epsilon, and reflectivity, all in a single inversion. So this is our approach. This is called multi-parameter FWI imaging, outputting at least these 2 products at every iteration. So how is it done? Well, this is the kernel that FWI is working with when we use the full wave field. And it contains the banana, which is here. This is the tomographic or velocity update coming from the diving wave. So this is what we're very used to using in conventional FWI. This is the so-called rabbit ears, which is the tomographic update coming from the reflections. And now I work for an Australian company, and I'm contractually obliged to call these roux ears and not rabbit ears. So both of these terms are coming from the kinematic effects, and these contribute to a velocity model update. And then we have the migration smile, which is the dynamic term and comes from the scattering interfaces. And what we're trying to do here is separating these terms out within MP-FWI imaging to get a separate velocity model from the tomographic terms and a reflectivity update from the migration smile. And if we do this correctly, then we should get an accurate velocity model and ideally a true amplitude reflectivity. And that's very interesting if we can do that, because it means that we can go from the field data to an interpretable product without having to go through that traditional processing workflow. And that means we have the potential to reduce project turnaround times, since we've bypassed many of those manually intensive and serial steps, each of which takes many hours or many days to test and apply. And more importantly, by using the more robust physics of FWI, we can do away with many of the assumptions that are inbuilt into that workflow, and that can give us better results too. And using all the information that we no longer have to throw away, the multiples of ghost energy, that means we can also get better coverage of the subsurface into our reflectivities, and that gives us better illumination and better resolution. So there are many benefits to trying to do this. And just to, I guess, press home what those benefits are, it's a least squares imaging solution, which means it can resolve illumination issues and improve resolution. As I said, it's using the full wave field naturally imaging with multiples. So there's a lot of extra information that we're using that we can interrogate the subsurface with and provide much more detailed images. And the use of reflections within MP-FWI imaging means that we are able to produce velocity models updates using a wave equation model building solution. And that can provide much more robust velocity updates compared to conventional ray-based techniques. So these are the primary reasons why I think this technology is the future of processing and imaging, but we don't have to wait 30 years because this is possible right now. In fact, it's a technology that we've applied to over 30 data sets worldwide now, and we can take a look at some examples from those. Now we're going to start with one of our earliest projects, and we've shown this a few times, but it's nice to demonstrate the full range of outputs and what you can do with this approach. It's from Western Australia, where we ran our MP-FWI imaging up to 80 Hertz. It's a conventional narrow azimuth towed streamer data set with a 6-kilometer maximum offset. So we have our MP-FWI imaging workflow where we take the field data, we go into FWI imaging to get simultaneously our reflectivity and our velocity. It's an approach where we step up through frequency bands, and the final frequency band here was a maximum frequency of 85 Hertz. Now, at the same time, we went through a conventional workflow where we took the field data, we went through the usual time processing sequence, and we depth migrated that data. We migrated with the same velocity model that we derived through MP-FWI imaging so that we could get a conventional stack that was comparable to our FWI imaging reflectivity. So first, I'm going to focus on one of the two outputs, the velocity model, and we're going to look at some conventional QCs to try and determine the validity of that velocity model. So this is the starting velocity model on the left, overlaying on a Kirchhoff migration of the processed data, just to give you an idea of the geology. It's fairly deep water at 1.3 kilometers. The initial model with a smooth legacy velocity model. Many of the examples here are using legacy velocity models as input. In the middle, you can see the well tie compared to the check shot, which is in black, the velocity in red. And on the right-hand side, you can see image gathers migrated using this initial velocity. And you can see there's a bit of move out on those gathers. So we know that there's work for us to do in the model building to generate a more accurate velocity model. Here are the same displays generated using our velocity model that we derived through 85 Hertz MP-FWI imaging. So you can see immediately on the right-hand side, the image gathers are flattening. It's obviously a good sign that we're getting an accurate velocity model update. You can see the tie to the well is improving, and the algorithm knew nothing about the well information. This all came from the data, all data derived. Just a nice QC to demonstrate it's going in the right direction. And you can see the impact on conventional imaging, most notably some lateral velocity variations. If I just turn on my pointer here. Some lateral velocity variations around this level that are resolving some push down, pull up issues in the deep and simplifying the deeper structures. And we're also capturing some thinner beds and thinner resolution in the shallow there too. So this kind of demonstrates the updates that we're able to get with the FWI imaging for velocity, and we could use it for conventional imaging if we wish to do so, but of course we don't need to because we also get a reflectivity volume out at the same time. And now we can have a look at that and compare that to our conventional stack. So this is a conventionally derived stack section of this data, an inline and crossline, where we've taken the field data. We've been through the workflow shown on the left, through deghosting, designature, demultiple, regularization. Typically, there's model building there too, but we migrated this with the velocity model that you've just seen using a Kirchhoff migration. So this is the conventional result, and this is the result that we derived through MP-FWI imaging up to 85 Hertz. And as we compare them, the first thing that we can see is the two are very, very similar indeed. And that's pretty remarkable given that the FWI imaging result has been through the workflow shown on the left here, has been derived directly from the field data without any of the processing steps that the conventional workflow has been through. Secondly, we can see in this image no sign of any multiples or the source or receiver ghost or the source signature. All of that was in the field data that we gave to FWI imaging, but none of it is shown in this reflectivity. That means this algorithm has essentially performed or handled for us, I should say, deghosting, designature, demultiple, model building, and least squares imaging in a single step to get to this result. It's perhaps unfair to call it demultiple because it's using that information to build this reflectivity. Now, they look pretty similar, but when we zoom in, we can see some clear increases in resolution. So this is a section view just beneath the seabed on the left, and we've taken a depth slice on the right through this complex layer in the middle here. And this is through the conventional imaging, and this is the result from MP-FWI imaging. So what we can see is an increase in temporal resolution on the left-hand side, more detail in and around the seabed, just beneath the seabed and through that complex layer. But most strikingly, we see a drastic increase in the resolution on the right-hand side of this display. And that's mainly coming from the fact that this is least squares imaging, and secondly, from the fact that it's using the full wave field, so using primaries and multiples to derive this reflectivity. You can see there's quite a drastic change going from something that's quite blurred, fuzzy, difficult to interpret, to something a lot clearer, more crisp, and better resolved with many more details in there. And this is a theme that we see, this increase in resolution through the use of least squares imaging and the full wave field. So you can see that in this example, we've gone from the field data to an interpretable product using this technology. We've got an accurate velocity model, we've got a reflectivity model. But what about AVA? We get more from the conventional workflow than just a single output. We also get AVA products. And well, we can generate AVA products with FWI imaging, with multi-parameter FWI imaging too. And we did that on this project. Here's an example of conventionally derived near, mid, and far angle stats through this data set, again, been through the workflow on the left. And here is angle stats that we've derived through multi-parameter FWI imaging. And again, as I toggle between them, you can see there's a strong similarity between the two. What's quite interesting is on the near angle stack in the deeper section, you can see the FWI imaging is a little bit cleaner. This is where the multiples would be appearing, and completely attenuating multiples on near angles can often be quite challenging in conventional workflow, whereas the more robust physics of MP-FWI imaging appears to have handled that a little better. So they look similar, but how do they compare to the ground truth? Well, we took well information, we derived some synthetics, which are shown in black here for near, mid, and far angles, as well as deriving P impedance and VPVS from our angle stacks and comparing that to the well information. And you can see the comparisons for FWI imaging in orange to the well information in black, and then on the right-hand side, the conventional angle stacks to the well synthetics. And you can see there's a good tie. There's a good tie between all of them, but it's interesting at this strong VPVS contrast marked by the yellow arrow that we can see that the FWI imaging is capturing that AVA anomaly a little bit better than the conventional Kirchhoff migration. That's leading to a better estimate of VPVS. And we even went through and pushed this through a full QI workflow where we determined P impedance, VPVS volumes, most likely lithology, and gas probability volumes with the conventional angle stacks at the top and the MP-FWI imaging angle stacks at the bottom. And you can see, again, a really strong similarity between the results, despite going through very different workflows using very different inputs, arriving at very similar results, including capturing and the gas-water contact in both examples, and the probabilistic volumes are indeed very, very similar. And so this gives us great confidence that we can get accurate amplitudes from this technology that we can use for AVA analysis. All right, let's move on to some other examples from different parts of the world. First of all, we'll have a look at an example from the Barents Sea. This was shallow water imaging for Aker BP using a half-size geometry, a very near-surface imaging. And for this example, we went even higher to 110 hertz to try and capture resolution in the very shallow. So what this is quite nice demonstration is, this is a nice demonstration of how the process iterates and how we move up through frequency bands and the benefit that that gives us as we move to higher frequency. Excuse me. So we're just going to focus on the reflectivity here, and I'm going to show you a result first of all. This is at 40 hertz, but we're looking at quite a narrow strip of data from the seabed at 400 meters down to a kilometer of depth. So only 600 meters of data that we're looking at, and at 40 hertz, that looks pretty low resolution. As we step up through the frequency bands, we start to see more and more resolution being introduced into this result. Here at 55 hertz, you see clearer structures. At 85 hertz, we're starting to introduce a lot more detail. And then at 110 hertz, a very high resolution result. So these are the outputs that we get during the process of this technology. This is one of the other benefits that we get from it, is that you don't have to wait to the end of the process to start interpreting and looking at your data. You get to see it evolve as you move through the frequency bands. What's quite nice about this is we compare this to conventional imaging. Again, this has been through the regular workflows. You can see on the left, I'll just toggle between those. Again, they look pretty similar, but again, we can see more resolution in shallow, especially beneath that strong black event, just beneath the seabed. There is some polygonal faulting that becomes a lot clearer when we look at some depth slices, which we'll do now. And again, we'll look through frequency bands here. So starting at 40 hertz, this is a depth slice on the left, just beneath the seabed. On the right-hand side, through those polygonal faults, it's quite fuzzy at 40 hertz. More detail at 55 hertz. Also at 85, start to see those polygonal faults on the right. And then at 110 hertz, we have a very high level of detail coming through in these depth slices. In fact, resolution down to within a few meters from the seabed on the left-hand side. And again, if we compare that to a conventional Kirchhoff migration, we see a much higher resolution, much sharper and crisper images coming through MP-FWI imaging. So that's a deep water marine, shallow water marine. We've even now been applying this to a land data set, which I can't say too much about. It's a project that's in progress, and these are kind of some early results. So, but I thought worth sharing because it's really interesting that this technology can also be applied to land data. There are a few more challenges with land. If we're using a viscoacoustic algorithm that we are here, then we have to deal with ground roll, and we have to deal with extra denoise and some surface consistent processing that isn't dealt with yet in FWI, but could be eventually. But these are really encouraging results at reasonably low frequency at the moment. This is an RTM of processed data through this land data set, and we have a section on the left and a slice on the right. And this is the result that we've got at the moment going through MP-FWI imaging on land data. And again, if I toggle between those, you can see it's a really dramatic increase and uplift in the quality, especially through the illumination in the deeper sections. It's much improved, again, thanks to least squares imaging. The imaging in the near surface that you can see on the right-hand side through that depth slice is quite stark. Lots more detail coming in, especially some faults and some channeling. The amplitude balancing is a lot better, and what we're even seeing as we iterate up through frequencies is the disappearance of multiples in the data, which can often be really tricky in many land data sets. Being able to use this technology as a demultiple tool, but again, using that information is really, really powerful. So it's really encouraging at this early stage. Pretty excited about what we can do on land data here. So a couple of other examples now, but this time from Gulf of Mexico. So deep water, Gulf of Mexico for salt imaging. And this is one of the areas where in complex environments, this technology can add a huge amount. So this is a wide azimuth acquisition with max offsets of 8 kilometers for salt imaging with a maximum frequency of 37 hertz. This is the legacy imaging, again, through the conventional workflow on the left with an RTM. And this is the result from multi-parameter FWI imaging. This is really quite a stark difference in the level of quality of the imaging that's being produced in this particular example. It is slightly higher frequency in the MP-FWI imaging compared to the RTM, so not an apples to apples comparison. But you can see many benefits in terms of the imaging, especially in the deeper section, especially around the deeper complex salt structures, and again, better illumination and amplitude balancing. What I like is in the central area, if we zoom in here, go between the legacy imaging and the FWI imaging, especially around some of these features in the deeper section here. Oops, sorry, what we see is a much better continuity of events with MP-FWI imaging. I think the main reason for that is the fact that it's this wave equation model building solution. So typically, once we've dealt with salt imaging in the near surface, we might generate surface offset gathers with RTM. We would use RMO picking and reflection tomography. But the ray-based approach or ray-based approximation of tomography has its limitations, especially in areas of complex geology, as we know. So using reflections in FWI and a wave equation model building solution allows us to get more accurate velocity model updates in those areas and better imaging. And so just to reiterate the two products that we're getting, this is just cycling between the two outputs from this project, the velocity model, and then fading out into the reflectivity. And you can see that these are the two aspects that we get. And I guess one of the things that we see is that the velocity is lower in wave number than the reflectivity, but we expect that if we look back to the rabbit ears that I showed you earlier, those are quite low wave number. And when we sum all those together, that's what we expect from the velocity model update. The higher resolution tomographic term goes into the higher resolution migration term, sorry, goes into the reflectivity, which is where the higher wave numbers are. All right, so one final example, another Gulf of Mexico data set, a project we undertook for Shell, OBN data this time, and a maximum frequency of 40 Hertz. So again, I want to just talk about the velocity model here. So what we're going to have a look at is the initial model and a conventional QRTM using that initial model of the process data, and then a QRTM of the process data using our updated velocity model. Now, in this example, the starting model was actually pretty good. It had been through a conventional workflow, and the FWI imaging was an add-on to the conventional processing, so it was in a pretty good shape to start with. But it had relied on the ray-based tomographic updates in the deeper sections beneath the salt. This is the starting model overlaying on the QRTM. And this is our updated model with MP-FWI imaging overlaying on its associated QRTM. Now, as I said, the starting model was pretty good, so the updates weren't dramatic here. But the largest updates and the most impact were made around beneath the complex salt wings, one of which you can see in the center there. We can see the shape of the salt is also changing. It's decided that the salt wasn't quite in the right position and needed moving. If we take away the velocity just to see the impact on conventional imaging, this is using the initial model, which again was in pretty good shape, and this was using the updated model from MP-FWI imaging. And so the changes aren't drastic again, as I say, but there are subtle and important details that are coming through, especially in those areas of complex geology. So better continuity of events around the edges of the salt and beneath that salt wing. Deeper events are coming through, as you can see on the right-hand side in the deep section there, and more coherent and consistent deeper events too beneath that salt feature. So all good signs that it's pushing the model in the right direction thanks to this more robust velocity model update approach. So again, we'll have a look at the reflectivity for this result. And again, we'll compare it to a conventional workflow of time processing. Now, that time processing workflow consisted of these steps for OBN data, shock carpet regularization, wavefield calibration, VZ denoise, separation, and down-down decon approach. Now, I guess the important thing here is that the input into the QRTM that we're going to put, the conventional QRTM, came from the down-going wavefield, mirror imaging of the down-going wavefield. It's often very difficult in conventional imaging of OBN data to simultaneously combine both up and down-going wavefields into a single output. So in areas such as the Gulf of Mexico, where we have sparse node acquisition, we might typically discard the upgoing wavefield and simply use the down-going wavefield and mirror image that. And that's what we did in this example into the QRTM. That fed into a single iteration image domain least squares QRTM. And then we used that as an initial reflectivity into a iterative data domain least squares QRTM. So we've got the full range of high-end imaging algorithms that we might typically apply in such a geological setting to compare to our FWI-derived reflectivity. So this is a section of the conventionally processed and imaged QRTM, the downgoing wavefield, been through the workflow again shown on the left. And you can see there's challenges with illumination here, especially around this shallow salt body and the salt wing, clear illumination issues beneath and in the kind of cones towards the edges. There are hints of deeper events, but it's quite hard to interpret what's going on here. Single iteration image domain least squares QRTM shown here. and if I toggle between those, you can see that we get an increase in resolution. Some of those illumination issues are starting to be resolved. It's done quite a nice job, and we can see better continuity of events beneath the salt. Then an iterative data domain least squares QRTM provides a further uplift in terms of illumination. If I toggle between the image domain and data domain least squares QRTM, we start to see some deeper events coming through as well that were previously pretty difficult to make out. But this does come at an increased level of noise and partly comes from residual multiple that's quite difficult to entirely attenuate in such areas of complex geology. So this is probably the most advanced imaging algorithm might get used in a conventional processing project. And now here's the result that we got from multi-parameter FWI imaging, and again derived directly from the field data without any of the processing steps of the conventional workflow. So if we can compare to the data domain least squares QRTM, you can see that we've got a reduction in noise. Again, the more robust physics of FWI is able to model and use the multiples that are present in the data. It's a complex setting. The resolution of the salt boundary and the sediments above has improved compared to the least squares QRTM, as well as an increase in clarity within the salt itself. And the illumination and continuity of events beneath the salt is also improved, with some of the deeper events now becoming much more visible than were previously the case. And again, one of the reasons for these imaging improvements is that the MP-FWI imaging is naturally using both up and down going wave fields that are present in the input data, whereas, as I said, the conventional imaging is just using the downgoing wave field. So it really is quite a dramatic uplift, especially when you compare it back to the QRTM, which is kind of a standard deliverable in such an environment, could take many months to arrive at this result. It's really a dramatic increase in the quality of the imaging without having to go through all those steps directly from the field data. So we've seen the improvements that this technology can provide over the conventional workflow. And as I said, the main reason for that is the least squares imaging using the full wave field to derive the reflectivity. So it's using a lot of the data that we have to process out before we proceed to conventional imaging algorithms. And so to try and demonstrate the challenges that this approach is having to overcome, we decided to do a test where we took out the time processing and we migrated the raw field data with a QRTM. And now there's a good reason why we don't migrate raw field data. That's because it looks really, really bad, as you can see here. But what it does is it highlights all of the challenges in the field data that we have to deal with in processing. So what we're looking at is a section on the left-hand side and a depth slice on the right-hand side. That depth slice is tracking the red line just beneath the seabed. And so what we can see on that slice is the impulse response from the receiver locations. The receiver carpet boundary is marked in orange, in purple, sorry, and the source carpet boundary is marked in orange. So what we see in here are evidence of the source ghost. So we have a black, then a white event at the seabed. There's also the source signature is embedded in there. And so we would need deghosting and designature to resolve that. A processing flow. We can see in the near surface, we've got poor illumination, especially evident from the depth slice. So we typically mirror image downgoing wavefield. That means the PZ summation and wavefield separation. We can see evidence of multiples in the deep obscuring primary, so we need demultiple there. And we've even got a missing receiver in the near surface on the top left there. And so that would require some interpolation to deal with. So what you can see here is basically the entire processing workflow that we've got to put this data through before we could successfully image it. Yet using exactly the same data that went into this migration and putting it into our MP-FWI imaging technology gives us this result here. It resolves all of those problems for us. So you can see that the seabed has gone from a white, then a black event to a single black event. Handling the deghosting, it's handling the designature. The imaging in the near surface is being resolved, especially evident from the depth slice on the right-hand side. That must be coming from the downgoing wave field. You can see the multiples are disappearing and the primaries are coming through in the deep. And it's even resolving and healing that near surface for us where we have a missing receiver without the need for any interpolation. So it's doing an enormous amount to overcome those challenges that we typically have to deal with in a processing workflow. The other nice thing is you can see on the depth slice on the right-hand side is the extension of the imaging well beyond the limits of the receiver carpet. And bearing in mind here that we're looking at this depth slice just beneath the seabed, tracking the seabed, and yet we're still getting a really nice image many kilometers away from the nearest receiver, right out to the edges of the source carpet. And that's all coming from the use of that extra information that we typically throw away. And again, if we compare back to a QRTM, again, you can see a step change in quality in the terms of the results that we can achieve here. So I hope these examples and what I've shown you here has demonstrated the power and potential of this technology. We're now using much more advanced physics than the conventional processing and imaging workflow in an attempt to derive accurate Earth models, including true amplitude reflectivities, as well as products that we can use for AVA analysis from the field data, as I've shown. Which is why I and many others believe that this is the future of processing and imaging. But where do we go from here? Well, what we're trying to do is build increasingly accurate physics into this algorithm. So the first obvious thing is elastic multi-parameter FWI imaging, which we are hopefully close to releasing. Other effects of modeling the acquisition as accurately as we can. That means including things like water column variations in our modeling, including tidal and current effects, all things that we're looking at right now, and many other things such as source and receiver array effects to try and accurately model the seismic experiment as best we can. And then there's great potential for this technology for time-lapse MP-FWI imaging, and then beyond that for developing uncertainty estimations through the technique as well, rather than just getting one output, getting an understanding of how likely that is to be the true answer. So we think there's great potential for the technology moving forward beyond where we are now. And that, I believe, brings me to my last slide. So yes, multi-parameter FWI imaging is a simultaneous model building and imaging. We're getting a velocity model and reflectivity from our FWI, full wavefield least squares imaging for improved illumination and resolution with minimal pre-processing, often no pre-processing, to get much better results and much faster. Thank you very much.